Okay, so when you're looking at a heating curve, we'll always have on the x-axis will be heat in calories, or sometimes it's time if we're adding heat at a constant rate. But the y-axis will always be temperature, usually in degrees Celsius. And what happens is, if we get a substance cold enough, it's going to be a solid. So here it is a solid, here it is a liquid, and if I heat up enough, it's a gas. So that's always true. You'll notice we always get this stair-step pattern that has basically two plateaus, a lower one between the solid and the liquid, and an upper plateau that separates the liquid from the gas. So when something goes from a solid to a liquid, we say it's melting, and when something goes from a liquid to a gas, we say that it's boiling. So you notice we'll always get these two plateaus. So again, below the lower one it's a solid, then it turns to a liquid, and then it turns to a gas. So when I'm asked to find what is the melting point, that's the temperature where it changes from a solid to a liquid. If I look here, that happens to be, in this case, of substance A, that's happening at 150 degrees Celsius. If I look at substance B, over here, I see that's happening at 300 degrees Celsius. Now, if I was asked what is the boiling point, the boiling point happens between where it is a liquid and where it is a gas. So it's the plateau in between those two values, the upper stair step, if you will, the upper plateau. So for substance A, that's happening here at 300 degrees. And for substance B, that's happening here at 450 degrees. Now, let's look at these next questions. Okay, it says, how much heat energy was needed to turn sample A from a solid at the melting point to a liquid at the melting point? Alright, so here I am, a solid at the melting point, and here I am, a liquid at the melting point, and it's this much energy that it took. So what we're looking for is this much energy. How much did it take to get from here to here? And if I look, since I'm counting by 25s on this axis, 25, 50, 75, 100, that would be 25, 50. So the answer is 50 calories. We'll try the same thing over here with substance B. How much heat energy was needed to turn sample B from a liquid at the boiling point to a gas at the boiling point? Here it's a liquid at the boiling point. Here it is a gas at the boiling point. So what we want to know is basically how far is it from here to here. And if we add up, we're going to see it is 25, 50, 75, 100, 125 calories. Remember, this axis is calories. Alright, let's see what we got here. Now we want to know what the heat of fusion is. The heat of fusion and the heat of vaporization. That's how much energy it takes to turn something from... Heat of fusion is how much does it take to get from a solid at the melting point to a liquid at the melting point per gram. So if you give me a gram of substance, how many calories does it take to melt it, to break up the crystals? So what I have to do is it took 50 calories to melt it, but now I have to see how many grams was in my sample. So if I look up here, I see that this sample here that I made this heating curve for, it was 120 grams. With that in mind, what I do is I take the 50 calories needed to melt it and I divide it by how many grams, 120 grams, and that gives me 0.42 calories per gram. So you had to add 0.42 calories to every gram of crystals in order to get it to melt. Now we're going to do the same thing for the heat of vaporization to see how much energy does it take to vaporize or boil each gram of sample B. So now we've already established for sample B that it takes 125 calories to get across here, but how many is that per gram? Well, I have 85 grams in my sample. So I have to take this amount of energy and divide it by the number of grams so I can say how many calories per gram. So therefore I have 125 calories. That's what we decided it took to get across that plateau to boil the substance in that sample, divided by the mass of the sample, which is 85 grams, gives me 1.5 calories per gram. Well, the second side is just more practice of the same thing. Let's see how you do here. Okay, so what is the melting point of substance C? So melting point is the lower plateau. It looks to me like it's negative 100. And if I say what is it for sample D, well, it's this little plateau over here right at 400. Look, I made a mistake because it was easy to miss. All right, for number 2, what is the boiling point? That would be the higher plateaus. So in this case it was 50 degrees Celsius. In the case of sample D, it was 450 degrees Celsius. How much heat energy needed to turn sample C from a solid to a liquid at the melting point? So that's how far across is this plateau here, and if we count across, because we're going by 25, so we get 150 calories. And if we do the same thing then for how much heat energy needed to turn sample D from a liquid to a gas, so here we're trying to go from a liquid to a gas, that's this much energy here. And that turns out to also be 150 calories. I'll make more coffee in a second, hon. Alright, so what is the heat of fusion of sample C? All I have to do is take the 150 calories needed to melt it, and then divide it by the number of grams, which is 24 grams. So when I do that, 150 calories to melt the sample divided by the mass of the sample gives me 6.25 calories per gram. Each gram required 6.25 calories to melt. Now if I do the heat of vaporization, I have 150 calories which is needed to vaporize sample D. But if I look up at sample D, what I'll see is it has a mass of 344 grams. And therefore, I have to say, alright, how much calories should it take? It took 150 calories per 344 grams. That's 0.44 calories per gram.